All right, we're picking up the second video on maintenance. Let's talk a little bit more about specifically the maintenance energy requirement, because that seems to be a big one. The biggest nutrient, well, it's not a nutrient, it's a product of nutrients, but the major requirement, nutrient product, that's the proper term, affected by maintenance is energy. It requires energy. And that's that measurement of that heat, providing direct estimate to how much net energy the animal must get from its food in order to meet those demands for maintenance. Remember, we talked way back when that we feed an animal gross energy. That's the amount that goes directly to the animal, it's offered to the animal. When we account for the amount of energy lost in the feces, that leaves us with digestible energy. Horses use an estimate of digestible energy for their energy requirement. Next, if we account for urine and gas loss, we're left with metabolizable energy, which is what pigs and poultry use. And finally, if we account for that heat increment and being able to account for heat production, that leaves us with net energy, and that's what the ruminants tend to use for their energy measure. So when we're talking about the maintenance energy requirement, we're looking at that measurement of heat that provides an estimate of how much net energy the animal really has to get to meet that demand for maintenance. And it starts with understanding basal metabolism. Basal metabolism is the amount of energy being used for maintenance. And remember, maintenance is survival. Just an animal that's not pregnant, not working, not growing. It's supporting the basic life processes of the central nervous system, the heart, the circulatory system, the digestion, absorption, metabolism, those types of things. It is sometimes referred to as a fasting metabolism in animals, and it is related to body weight. Many years ago, research was done that found a relationship between body mass and total metabolic rate. And to be able to truly evaluate animals on the same playing field, it's standardizing for surface area, essentially. It relates to the surface area ratio of the animals. Because that surface area allows for that heat to be given off, and it allows us to estimate energy. When we talk about smaller animals, think mice, rodents, those types of things, comparing them to beef cows or elephants or whatever larger animals we want to talk about. On a per unit of body weight basis, smaller animals have higher metabolism. They have a higher metabolic rate, they burn through nutrients faster. Small animals tend to have a greater surface area, which allows for greater heat loss to the environment, which allows for them to require more energy. And so they've got to work harder to maintain that constant body temperature because they've got more surface area and more heat coming off and going to the environment, so they can't retain that heat to maintain temperature, so that results in a higher metabolism rate. Surface area, if you want to try to figure out how to measure the surface area of a cow, go for it. It is super hard to measure. But what we can do is we can predict surface area from what we call metabolic body weight. And metabolic body weight was derived during that original research where we were comparing surface area of animals and energy expenditure. And it's a standard number. It is body weight to the 0.75 power. Understanding that for most species, it's body weight in kilograms. And so if you're looking at requirement tables and it says energy requirements in metabolic body weight, and you need to have metabolic body weight to determine the requirement, that is the live body weight to the 0.75 power. This is what's defining that metabolic size of the animal, or that surface area of the animal, which is to get a little bit more accurate description of that surface area and how much energy expenditure that animal's really going through. And so when we're comparing different animals, we on different metabolic size, or based on metabolic body size, that body weight to the 0.75, what we find is that basal metabolism is actually similar. So this allows us to compare animals and to develop requirements that allow take out some of the animal factor and that variability. It allows us to treat animals the same and put them all on the same playing field, so to speak, as we evaluate their energy requirements. So we have, when we talk about maintenance energy requirements for the livestock species, these are some formulas, and we do need to practice these to some extent. Beef cattle utilize, looking at net energy for maintenance, right here, okay? And so say if we have, it's a standard formula of 0.077 times body weight to the 0.75. This is where body weight is in kilograms per day and net energy is in megacalories per day. An example of this, if I'm grabbing my calculator here, is say if we have a 700-pound steer, okay? If we convert that to kilograms, which would be 700 divided by 2.205, which would be 700 divided by 2.205. That gives us a 317 kilogram. If we take that to the 0.75, that gives us a metabolic body weight, 317, finding it on my calculator here because I'm doing this as we go. That says that we have a 75 kilogram metabolic body weight. Okay, so to finish with this equation, we can take that 75 times 0.077, which is the amount, how many megacalories per unit or per kilogram of metabolic body size. So 75 times 0.077 tells us that that growing beef animal that's 700 pounds requires about 5.8 megacalories of net energy for maintenance per day. So we can do that with any of the beef species. It doesn't matter if they're a mature beef cow or a growing steer. It doesn't matter because maintenance is the same. It's when we start getting to the production differences that we'll have to have different equations. But that's an example of beef cattle. Sheep have a similar equation where the only difference is that net energy is in kcals per day and body weight is still in kilograms. So if we were to do an example for a mature ewe, say a 200-pound ewe, if we divide that by 2.205 to get to kilograms, we find that that 200-pound sheep is really, whoa, and I typed in a number wrong because she's not 975 kilograms, divided by, yeah, multiply versus divide makes for a big difference. She's a 91 kilogram sheep. If we take that to the metabolic body size, we find out that that 91 kilogram ewe is really, her metabolic body size is 29.5 kilograms metabolic body size. Okay? And so if we take those units times 56, because it's 56 kcals per unit of metabolic body weight, we find out that that sheep really requires 1,652 kcals per day of net energy for maintenance. So that's an example of how these equations work to be able to estimate those energy requirements. Swine is similar. Just understand that the units that swine are in includes metabolizable energy. And so from the standpoint that it's not net energy like the cattle are, it's metabolizable energy for maintenance. And so it's the same thing. Convert it, the body weight, to kilograms and take it to the 0.75 power and multiply that times how many kcals per unit. Horses are the only funky ones that actually do not use the metabolic body weight. They opt to just use body weight. So when we take a look at the horse equations, there's one for the light horses, and then one for the heavier horses, the draft horses, and some of the cold blood species. And so if you notice, body weight is just plugged into an equation. You have two different equations. They both estimate the digestible energy for maintenance in megacalories per day, and the body weight is in kilograms. But it's the only one that does not use metabolic body weight. Sorry, as I'm writing sideways there. But it's the only one that does not use metabolic body weight. And so you should be able to plug into these equations the numbers and estimate the digestible energy for a horse. That wraps up this second video on maintenance.